In this video, we'll take a look at the force between two currents. Specifically, we'll look at the force between two parallel currents, as that has some symmetry. We know that a current flowing through a wire produces a magnetic field, so it should be able to produce a magnetic force on any other object that creates a magnetic field. So it should be able to create a magnetic force on another current-carrying wire. Let's take a look at the magnetic field produced by the current flowing through wire A. And we'll look at the magnetic field towards the center of the wire where we have additional symmetry. So this magnetic field was going to form a closed loop. It's going to have a circumference of 2 pi r at some perpendicular distance r from our wire A that's carrying current IA. So if we look at the distance d, since that's the distance between these two wires, if we look at the radial distance d from, so this will be d and this will be d, for this magnetic field loop, we see that the magnetic field at wire B will be pointing in the downward direction as shown here, and that will be the magnetic field BA produced by wire A. The force then on wire B depends upon its magnetic properties, and the magnetic properties at wire B have to do with the current flowing through the wire. So we can use our force IL cross B rule to determine that force. And if we do, since we have current flowing in this direction and our B flowing or pointing downward, then we can rotate and we get the direction of our force on wire B due to the current flowing in wire A is going to be towards wire A. And we're using two different, a right-hand curl for the direction of the magnetic field magnetic field produced by current A, where we're pointing our thumb in the direction of the magnetic field from our right hand, and in doing so our fingers curl in the direction of our magnetic field. Always perpendicular to that magnetic field line is the magnetic field. So another way to look at this, easier in a plainer sheet of paper here, we have IA and IB. We demonstrate the X. The X means that they're flowing into the page like the tail of the arrow. So we have two parallel currents, IA and IB, flowing into the page. IA again is producing a magnetic field. This distance, this radial distance here between the two wires is D, and so is this distance here, D. And that radial distance, if this is the radius of our field, is perpendicular to the magnetic field at any point on the magnetic field line. So we see that at position of wire B, our magnetic field pointing downward, and then we get our force then to be pointing towards wire A. Similarly, if we look at the magnetic field produced by wire B and we do our right-hand curl, we see that that magnetic field is going to be going also clockwise, and at wire A it's going to be pointing upward. Since the current at wire A is into the page, if we point our fingers into the page and then curl up, we get our force pointing inward also. So we get the fact that these two parallel currents are attractive. So if we want to find our procedure then to find the magnetic field produced by current A at wire B, we have our magnitude of magnetic field, mu naught IA over 2 pi, that distance r is D. We do our right-hand curl and find that that direction is downward. Then we determine the force that this magnetic field BA produces or exerts on wire B, and we can use our IL cross B. L then is the length of this wire, and because these two wires are parallel, that L is perpendicular to our magnetic field B because they're parallel currents. And so then we can find the magnitude of the force. Magnitude of the force is IBL BA. Substituting in for BA, we get the product of the two currents is what produces the force. The distance between them, 2 pi times that distance between them, that's going to be the radius of the magnetic field line at that point. And we have L. So sometimes we'll write FBA over L is just equal to our mu naught IA IB over 2 pi d, where we look at the force per unit length on the wire. So again, our direction of that force then we also find with the right-hand curl, where we curl our I, again in the direction of B, we find this force pointing towards. So we have parallel currents attract. Parallel currents attract like opposite poles attract. And we show in this diagram both magnetic fields at the same time. Both these magnetic fields current flowing into the wire are clockwise. At wire B, magnetic field due to wire A is pointing downward. At wire A, the magnetic field due to wire B is pointing upward. And we have the equal and opposite attractive forces. FAB is equal to FBA and Newton's third law. What happens if the currents are anti-parallel? Well, anti-parallel could be the case if the two wires are in fact running parallel to each other, but here we show IA coming out of the page and IB going into the page, or anti-parallel could also be IA going into the page and IB coming out of the page. So let's look at the scenario. What is our magnetic field going to look like here due to IA coming out of the page? So now doing our right-hand curl, we point our thumb towards us, our right thumb, then that magnetic field BA up at the top is going to be pointing in this direction. It's going to be everywhere, again, perpendicular to this circle of circumference R, or D if we want to call it the distance between these two wires. So there's our magnetic field also. And once we at wire B, that magnetic field is going to be pointing upward. And since our current of B is flowing inward, if we do an I cross B, we get our magnetic force here. The force on B due to A is going to be pointing away from A. Well, there's no change. IB is still flowing into the page, so our magnetic field at IA is still going to be pointing upward due to, or that's going to be the direction of the magnetic field at a distance D away from our parallel wire B. So our magnetic force here, if we do our right-hand curl, will be pointing away. So now if we look at this other similar scenario where we have anti-parallel currents, in this case our magnetic field due to current in A, when we get to IB, well, that's still going to be pointing downward. So there's our BA. That's the same scenario, but now our current IB is pointing towards us. So when we do our I crossed with B with our right hand, we have our FBA pointing in this direction, and I'll let you do that on your own, but you'll find that this current will also have a repelling force. So what we find about anti-parallel currents repel similar to how like poles repel. And here we show on the same diagram the magnetic field in red due to the current flowing through IB in wire B, the magnetic field in blue due to the current flowing in wire A due to current A. And we have repelling forces. Those repelling forces are like the north pole and north pole of a bar magnet, they will repel, or the south pole and south pole of a bar magnet, they will repel. Anti-parallel currents will repel if IA is flowing towards us and IB is flowing in, or if IB is flowing towards us and IA is flowing in. So in general, the magnitude of the magnetic force, FBA, will be equal to FAB. It'll be equal to, proportional to the length of the wire, so we could find force per unit length. It'll be inversely proportional to the distance between the two wires, and be proportional to the product of the two currents. And of course we have our proportionality constant mu naught, which is our permeability constant in a vacuum. So we have parallel currents attract and anti-parallel currents repel. Another way to look at these diagrams is if we show the magnetic field, instead of showing it as a loop, a ring, we can show it on either side of the wire. So here if we have our current I1 flowing to the right, then the magnetic field produced by that will be flowing down here. If we on this side of it, it would be flowing towards us, right? This would be our B1, but we're concerned about what it is down here at the other wire, so that's where it's going to be flowing in. So we have magnetic field flowing inward due to B1 at wire 2, and we have the magnetic field also flowing inward due to I2 at wire 1. So up here we show B2, down here we show B1. So on this side, of course, we have, if this was our B2, it would be flowing in this direction. So then we can do our cross product and also show that parallel currents attract, anti-parallel currents repel. So just another way to draw the diagrams. So let's look at the definition of an ampere. Ampere is one of our 7 SI base units. We said it's a coulomb per second, but it's not defined based on a coulomb. In fact, it's defined by the force on the wire. So 1 amp is the constant current that, if maintained in 2 straight parallel conductors of infinite length, of negligible cross-sectional area, that are placed 1 meter apart in a vacuum, they will produce a force on each other of 2 times 10 to the negative 7th Newton per meter of length. So if we had 2 parallel currents, negligible cross-sectional area, distance d 1 meter apart, each carrying a current of 1 amp, then our magnetic force per unit length, our mu naught, 4 pi times 10 to the negative 7 Tesla meter per amp. Our current's both 1 amp, so we have our 1 amp squared divided by 2 pi times 1 meter. We get 2 times 10 to the 7th Newton meters. So we end up with the 2 pi's, right? The 2 pi cancels from the mu naught, and we end up with a 2. So that's our definition of an ampere. Another important application of these parallel currents is a rail gun. So if we look at a rail gun, we have current, typically a very large DC current, that runs up through a conductive rail, and it's a big rail so it can carry a large amount of current, and then it passes through a loop. In order to get around a loop, we have a conducting fuse, and it comes back, and then back here is whatever your source is. We'll let the source, in this case, be a battery, so maybe we have some battery tied here, producing this current. It could also be a capacitor. As that current flows, if we take a look at this diagram, we can see the direction of the magnetic field due to both of these currents between the 2 rails is going to be into the page. We show that with an X, and you can show that with your right-hand curl. So if we have here a magnetic field flowing into the page and a current flowing to the right, then our magnetic force is going to be pointing upward. And that magnetic force then is going to have the effect of propelling, right? It's also a gas, so the gas can explode, but it will propel this projectile. So showing this figure in terms of showing our circular magnetic field lines, and showing our projectile there. So we also know that these are anti-parallel currents, right? So anti-parallel currents repel each other, so the magnetic force on each of these rails down here is going to be outward. So that's going to have the effect of pulling these rails apart and giving this projectile up towards the top. It's going to require even more force to push that through. So these conducting rails can produce huge amounts of force. The recently announced the U.S. may field a rail gun and the Zumwalt destroyer. Here's a link to that. It converts electromagnetic energy to kinetic energy, and a projectile speeds on the order of Mach 7, 5,000 miles per hour. Lighter weight and less expensive than current missile system, but it requires about 25 megawatts of power. Also, the U.S. Navy is considering a railgun to launch